Welcome to the lesson 40 of industrial instrumentation. This lesson is basically we will consider some of the signal conditioning circuits which are available in IC chip form. As you know that there are some sensors like LVDT, thermocouple, we need some conditioning circuits. In the case of LVDT, we need some circuits for null voltage reductions, we need some circuit for the phase compensation, because in LVDT always there is an input output phase difference. So, that can be killed only in the by using some signal conditioning circuits, because in null voltage also we need some lead lag network type of things for the phase compensation. That means, if I want the input and output should be at the same phase, right, because we need some excitations in the case of LVDT. Now, similarly, we have also in the case of thermocouples, we need cold junction compensation. For that reasons, we have already discussed some chip like AD580. Okay, so that has some advantages, maybe AD590. So, but there are some more chips. Some chips came out which has more has a better performance. Similarly, we will also discuss this the current voltage to current converter, which is also available in the chip form. One thing I should mention, that you can do it with discrete component, but obviously, if you use some CMOS chips, you will get some additional advantages. It is off the shelf devices, you can take an interface with your either LVDT, your transducers, so for better results or better performance. So, in this context, this lessons is actually signal conditioning integrated circuits, right. So, basically signal conditioning circuits you have already defined, already discussed. Some filters, some amplifiers, those things we have already discussed, some logarithmic amplifier, anti-logarithmic amplifiers, sample and hold circuits, all these things we have discussed. But in this particular lesson, we will consider some of the shelf chips, right, which are very handy. We can use it for signal conditioning purposes. Let us look at the content. Contents are, we will discuss first LVDT signal conditioner, then we will look at cold junction compensator, because I know that cold junctions is a problem in the case of thermocouple. Because it is industrially a cold junction is not possible. That means, one junction cannot be put in ice. So, there is always a variations of the one junctions, and measure junctions accordingly, whatever the temperature we want to measure, accordingly it will vary. But cold junction cannot be put in ice bath, it is not possible. So, for temperature change, I need some compensation which will correct that temperature change, right. So, that is a cold junction compensator. And thirdly, we will consider the voltage to current converter. In many situations, we will find that we need to convert this voltage 0 to 5 volt or 0 to 10 volt to the 4 to 20 milliampere or 0 to 20 milliampere. So, in that type of, because industry, as I told you several times, that always we need 4 to 20 milliampere of signal conditioning currents. So, that type of situation can be handled only if I have a power current, because we never transmit the voltage in industries, always in any transmissions we need current to transmit. So, in that type of situations we always want the current. So, any voltage is to be converted to the current domain. So, standard practice 4 to 20 milliampere. So, we can do it with the discrete components, but obviously, we can do better with the IC chip, right. So, this all we will discuss in this particular lesson. Let us first look at the LVDT signal conditioner. Now, LVDT, you know that how does it look? Let us make a brief recapitulations. It will look like this. I have a primary, right. I have two secondaries are there, and I have a core inside, is not it? That is our LVDT. So, I put a excitation here, and I will get two secondary voltages here. This is the basic diagram of LVDT, right. I will put a displacement here. Please note, LVDT is electromechanical sensors, and it basically a displacement sensors. Directly it is measuring displacement, but it can measure so many other. Indirectly it can measure pressure, it can measure many other parameters, right. So, the basic it is displacement. Now, I am giving an excitation. This all those things are very deeply discussed or very widely discussed in the case of LVDT. the lesson of LVDT, but here actually I mean I am just making brief discussion to have a good recapitulations of our LVDT. Now, if I you see if I move this core up and down, so there will be a linkage. If I put this LVDT up, this core up, there is a more linkage between primary and secondary. If I put it down, there is more linkage between primary and this secondary, right. So, 2 voltage I will find the voltage will be different. Now, if I put this in opposition, in series opposition like this one, so what I will get, the output voltage will be a function of output voltage, a function of the displacement x. At mid positions, at geometric mid positions, I will get a null voltage. I will get a 0 voltage, rather I should get a 0 voltage, because these two secondaries, these two voltage will cancel out each other. So, I will get a supposed to get a 0 voltage, but due to mismatch of the secondaries always will get some non-zero voltage, right, due to mismatch of the secondary. If I look at the 2 secondary, I mean looks like this. Suppose this is IS1, one current is IS1, one secondary current is IS1 and one secondary current is IS2, right. But you will find that the 2 current will exactly will not be, it is very difficult to make a 2 identical magnetic circuits, right. So, 2 voltages will never cancel out each other. So, there will be a certain residual voltages. That voltage, now if I plot this LVDT, as we know, these all things we have discussed, as I told you several times, x, this is output voltage E naught. So, the response will look like this one. Okay. It should be a straight line, because LVDT is a linear straight line like this one, clear. This is output voltage. So, if I make a displacement, if I measure the magnitude, it will look like this one, because it is AC voltage. So, I will get an amplitude. So, this will be plotted. Clear? So, this will give you our basic LVDT. Now, you see there is always some null voltage which will appear. We have also shown there is an input output voltage, sorry, this will be Ex, I am sorry, this will be our sorry. So, this will be actually Ex excitation, right. Now, for this movement you will always find there is a output voltage, and this excitation voltage there is a phase difference between input and output, which is undesirable properties. Now, all these things you will find the null voltage cancellation, and always whenever you are using an LVDT, I need a separate excitation voltage, right, separate, because that is like a bridge. As you know, we use a Wheatstone bridge. Wheatstone bridge also need an excitation, either DC or AC, it does not matter, but in the case of LVDT, since we are using transformer, so always there is an excitation. So, this can be easily avoided if I use a particular chip available, right. So, this excitation also inherently you can vary the frequency of excitations, right, and I am getting output voltage which is free from all these problems. Let us go back. Now, the input to LVDT, which is linear variable differential transformer, is a displacement of the core, and its output is a pair of AC voltages proportional to the core position. As we know, this is basic LVDT. It is an electromechanical transducer consisting of a primary winding energized by an external sine wave reference sources, external sine wave reference sources, please note always we need this source outside, and 2 secondary windings are usually connected in series opposition. This we have discussed in details when we covered the LVDT. The movable core change the flux linkage between the primary and secondary windings, which is giving a non-zero output voltage E naught. Now, LVDT signal conditioner circuit is AD598, it highlights of the chip, what are the, so this is the chip number is AD598 developed by the analog devices. AD598 is a monolithic IC to be used with an LVDT for signal conditioning purpose. A complete transformation of displacement or mechanical position to DC voltage, both unipolar and bipolar, is possible, okay, directly, because we have seen that to make it sensitive, phase sensitive, I need a phase sensitive demodulator. So, those things also can be eliminated if I use this AD598. So, three most important things which we need to use an LVDT. I need a, first of all I need a source, okay, excitation voltage is necessary. I need is a null voltage, null voltage reduction circuit that will make the null voltage 0. That means at the geometric position 0 position there should be the 0 null voltage. Thirdly, I need a phase sensitive demodulation circuit. That means phase sensitive demodulation circuit is something like that, on which side of the null position the core lies, it will be detected by the phase sensitive demodulation circuit. That means, if I look at, if I use an LVDT, you see that we have seen that if I put a displacement x, I will get a circuit output like this one. So, on you see on both, this is a null position, this is a null position, this is output voltage 0. On both side of the null, I am getting a non-zero output voltage. So, it is very difficult, looking at the voltage it is very difficult to tell on which side of the null actually the core lies. So, what I can do like this one. So, if I use a phase sensitive demodulation circuit, this is a circuit with output voltage E naught with phase sensitive demodulator, phase sensitive demodulator, right. The output will look like this one, clear. So, for looking at the voltages or the polarity of the voltages, I can tell whether which side of the null the voltage lies. So, all these things is incorporated in 8599. So, it is a great, so many external components will be saved by using a single chip. So, 8598 is a monolithic IC to be used with an LVDT for signal conditioning purpose. A complete transformations of displacement or mechanical position or DC voltage, both unipolar and bipolar, is possible with this, and it can be used also for RVT, rotational velocity displacement transducers. Okay. This is also possible with this type of device, with this type of chip. 8598 accepts a wide range of input and output voltages. These are all the features what we can, and frequency. It can drive an LVDT primary with up to 24 volt RMS and accept secondary input levels as low as 100 millivolt RMS, right. Hence, it can be used with almost all types of LVDT. That means, you see that LVDT, the primary can go up to 24 volt RMS. The excitation frequency is determined by a single external capacitor, okay, by using a single external which is outside the chip, by excitation frequency of the LVDT can be determined by a single external capacitor. The range is 20 Hz to 20 kilohertz. Moreover, the input signal need not be synchronous with the LVDT primary drive. Thus, an external primary excitation of any desirable frequency can also be used, right. This is another most important thing. The ratiometric decoding scheme used by the 8598 is such that the ill effects caused by the primary to secondary phase shift that I told you will be eliminated, and transducer non-zero null voltage do not influence the overall circuit performance. Okay. So, it will be independent of the non-zero null voltage, which is obvious in all LVDT, because you cannot make two LVDT secondaries exactly same, right. So, it's a little dissimilarities of the two secondaries will give us a non-zero null voltage, okay, which is can be measured very easily in an LVDT if we use without any signal conditioning circuitry. The 8598 can be used in telemetry to the interface electronics when it is far away from the LVDT, and it can drive an LVDT at the end of the 100 meters of cable, and the position output can drive as much as 300 meter of cable. I think it will be cable if I am not wrong. So, it will be cable, right. The excitation output of 8598 is thermally protected, and 8598 can drive the multiple LVDT in either series or parallel as long as power dissipation limits are not. This is a great advantage. You see, the same LVDT, same chip can be used for several LVDT excitation. So, that is a great saving in cost. It can be used as a loop integrator in the design of the electromechanical servo loops. Theory of operations, let us look at a functional block diagram AD is shown, the figure 1, and 8598 energizes the LVDT primary, senses the LVDT secondary output voltage, and produces a DC output voltage proportional to the core position. That is actually ultimate result. That means, for different core positions I need a DC output voltage. Why DC? Because I need a DC because I have to make the phase sensitive. On which side of the core which side of the null position the core lies, that I must know. So, that only can tell by the polarity of the DC voltage, right. To drive the LVDT primary, AD598 uses a sine wave oscillators and a power amplifier. It also consists of a decoder which determines the ratio of the difference between the LVDT secondary voltage divided by their sum, and a filter and output amplifier. These are used to produce the DC output voltage proportional to the core position. You see, this is a block diagrams on the LVDT, right. LVDT, our AD598. Okay, this is actually inside the chip. You can see this portion. This portion is inside the chip. This portion is inside the chip, right. And there are pin numbers 2, 3. So, 2 and 3 will be connected to the primary of the LVDT, okay, and 10, 11 and 17 will be connected to the two secondaries of the LVDT. 10, 11 are two extreme point of the secondaries, and 1 will be connected. Two secondaries will be connected like this as it is shown, and it is grounded, and these two signals are coming to a signal conditioning circuits which will make two signals. That means A minus B divided by A plus B means that means VA, actually it is VA minus VB divided by VA plus VB, ratiometric principle as I told you. So, this will make, when the two voltages are equal, obviously this should be 0, right. That means the output voltage will be 0. So, output voltage will come out as a 0 here. So, filters and amplifiers, and this is an oscillators and amplifier. Okay. To have a stable oscillation, what they do actually in the case of LVDT, they first make a generate a triangular wave. Okay. They generate a triangular wave, then with the signal processing they convert the triangular wave to approximate sine wave, okay, because a triangular wave can be converted to a sine wave. Then it is fed to the amplifier, then it is feeding to the primary of the, this is the primary of the LVDT, clear. Now, how you do it? You see that if you can look at it, looks like this one. So, triangular waves are like this. So, with diode I can round off this value. So, it will look like this one, like this one, though it is not exactly sine wave, but for most of the purposes it will suffice. It is a continuous form. There is error, if you look at that, there is a distortions and all this, it does not matter, it hardly matters, because nobody say that you exactly you have to use the sine wave there, right. And this frequency of this is determined, of this triangular wave is determined, or the sine wave, approximated sine wave is determined by an external capacitor, clear, right. So, this voltage will be divided by A plus B. So, it will give you the filter. This is a block diagram, but inside there is a much detailed circuit. This is a chip pin diagrams. We can see that it is a 20 pin DIP, 12 pin line packages. So, we have all those excitation lines 2, 3, we have filter lines 8, 9, we have output filters, then we have signal output. So, this basically two excitations will give to primary, and we have a dual supply V plus Bs and minus Bs, okay. Either single ended, if you need single ended, this is to be grounded, that means if I need only unipolar, so this is to be grounded, and this output is signal output will come out. You can take the output filter also, okay, and signal differences, right. This is our pin diagram. The oscillator consists of a multivibrator, because multivibrator, as you know, multivibrators frequency, I can use Wien-Bridge oscillators and all these things, but multivibrator frequency will be more stable. So, that is the reason they use a multivibrator, which produces a triangular wave output. The triangular wave drives a sine shaper, which produces a low distortion sine wave, whose frequency of oscillation is determined by a single capacitor. So, I challenge this one, it is not exactly the low distortion sine, there will be distortions, it will not be a pure sine wave. So, there will be a certain amount of distortion lies there. As I told you, it does not matter much, right. Output frequency of the oscillator or oscillator ranges from 20 hertz to 20 kilohertz, and the amplitude from 2 volt RMS to 24 volt RMS. Total harmonic distortion is typically minus 50 dB. The output from the LVDT secondaries consists of a pair of sine waves whose amplitude difference is V A minus V B and is proportional to core position. This will be proportional to our core position, because always in LVDT we want like that. The previous LVDT signal conditioners, whatever, because we knew already we did this type of things, we made a lot of adjustments of the, we need a, as I told you, we need some signal conditioning circuit to kill the null voltage, to kill the phase difference between input and output. Previous LVDT signal conditioning circuits rather used to synchronously detect this amplitude difference and convert the absolute value to a voltage proportional to position. This technique uses the primary excitation voltage as a phase interference to determine the polarity of the output voltage. There are a number of drawbacks associated with this technique. We had to produce a constant amplitude, constant frequency excitation signal, which is very difficult. Okay. You see, this is very important. While you are measuring with LVDT, always we are telling that the amplitude of the input voltage should remain constant, right. It is not it. If the amplitude of the input excitation voltage falls, then what will happen? Like this one, suppose if I tell that it will happen, what will happen? Suppose I have an LVDT. So, this voltage should remain constant, excitation of the EX will remain, amplitude of the EX should remain constant, it should have a constant frequency also. Otherwise, what will happen if suppose for some reason this amplitude falls, this output voltage also will fall. Suppose this is series opposition, output voltage, that is undesirable, because only the output voltage amplitude will tell me the exact position of the core. So, I will get some ambiguity, but that is not possible in this particular chip, because we are using ratiometric principle. They are using some ratiometric principle. So, it does not matter, I mean if the input voltage frequency falls or rises, okay, automatically output voltage will be independent of that. So, I do not need a constant amplitude, constant frequency signal, right, though it is internally generated, but some reason or the other if the amplitude falls, it does not matter. This technique requires compensation for LVDT primary to secondary phase shifts. This technique requires compensation for LVDT primary to secondary phase shifts. Also, these shifts varied as a function of temperature and frequency, adding to the complexity of the compensation method. Okay. So, this all thing can be avoided. So, AD598 eliminates all of these problems. Let us take one by one. It does not require a constant amplitude, because it works on the ratio of the difference and sum of the LVDT output signal. So, automatically it will cancel out, right. So, any change, any variations of the input excitation voltage, frequency, and it will be automatically cancelled out. A constant frequency signal is not necessary, because the inputs are rectified, only the sine wave carrier magnitude is processed. Input voltage will be rectified and the sine wave carrier signals will be processed. The phase shift between the primary excitations and the secondary output is not important, because the synchronous detection is not employed, right. This is another advantage. The ratiometric principle used in AD598 requires that the sum of the LVDT secondary voltage remains constant with LVDT stroke length. Okay. Stroke length means that length through which the LVDT travels, right, that is called the stroke length. Now, next signal conditioning circuits I am going to discuss is the thermocouple signal conditioners using 8594 and 8595. Okay. Because some, I mean thermocouples, always we have seen that we need a cold junction compensation, which is a headache for thermocouple, because ambient temperature may vary, but that does not influence my reading. Suppose I am reading a thermometer with a thermocouple at temperatures of 700 degree centigrade. If my ambient temperature varies from 5 degree to 40 degree centigrade, it should not influence my reading. So, that is only possible if I use this type of cold junction compensation. Cold junction compensation chip was already there, but this is the improved chip, okay, compared to the whatever the cold junction compensation chips, and it eliminates many additional circuitry which is necessary along with the 8590 or 580. And features of the chip: it is a pre-trimmed for J type or type K thermocouple. As you know, industry we always call thermocouple by J, K, SRT, depends on the what particular alloys they are using. So, it is pre-trimmed for For J type it is 8594, for K type which is most widely used thermocouple in industry. Okay. It can be used with type T thermocouples inputs also, which is a platinum rhodium thermocouple. Platinum rhodium thermocouple, I should say. Platinum rhodium is a positive voltage and negative, and platinum is a negative. It has low impedance voltage output of 10 millivolt per degree centigrade and a wide power supply range of plus 5 volt to plus minus 15 volt. It has built in ice point compensation. Okay. It has inbuilt devices like thermocouple failure alarm, because if the thermocouple junction is open, so that some alarm should be given, which is not their previous thermocouples. It will give some alarm, some voltages which can be energy which can be used to some trip some alarm, so that the person in the process know that this thermocouple is out of order. And a self-contained Celsius thermometer operation is also possible. Okay. Direct readings of the thermometers in temperature degree centigrade is possible. There is another advantage. It has a low power, it is less than 1 milliwatt typically, and high impedance differential input is there. So, common mode noise problem can be immediately eliminated. Basics of thermocouple. One of the most widely used devices for temperature measurement is a thermocouple. It works on the basic principle that when two dissimilar metals are joined at both ends, just have a short or brief recapitulations of the thermocouple. Thermocouple we have covered in details, but let us have a small discussion, because all these chips are related to the thermocouples. This particular two chips what we talked about is related to thermocouples. So, let us briefly discuss principles of thermocouple. It works on the basic principle that when two dissimilar metals are joined together at both ends, one end is heated, a current will flow. Now, if the loop is broken and the center and open circuit voltage Seebeck voltage is generated and is proportional to the difference in temperature between the two junctions. We all know this thing, right. Therefore, and in determining the temperature of the measuring junction, the reference junction temperature must be known, right, because it is the difference of temperature which will actually give us the voltage, right. If the two junctions are the same temperature, output voltage will be 0, right. So, the difference, that means the ice point or the reference junction temperature, which is not varying, which is supposed to be at the ambient temperature, should be known. An ice bath provides a well defined temperature of 0 degree centigrade for reference junction, but that is not possible in any process industry. Okay, this we can see the thermocouple loop. You see, I have a measuring junction here, right. I have a measuring junctions. Let me take this one. I have a measuring junction here. Okay. I have a reference junction. This is at ice point at 0 degree centigrade. Okay, degree centigrade. I have broken. If it is not, if no voltmeter is connected, then what will happen? I will get a current through it. Okay, but if I break it, so open circuit, so I will get a voltage. So, this voltage is proportional to the difference of the temperature T1 and T2. That means that VT1 minus VT2 is a function of T1 minus T2. As the temperature is higher and higher, temperature difference is higher and higher, T1 minus T2 is higher and higher, I will get a higher value of the voltage VT1 minus VT2, right. This is the basic principles of a thermocouple. A voltmeter is used to measure the voltage developed as shown in the figure, and two additional junctions J2 and J3 are formed at the connection between the thermocouple connecting wires to the meter, because that cold junction is not there in industry, as I told you. Excuse me. These two junctions produce opposing voltage within the thermocouple loop, right. So, one of the most important thing is that you have to, this should be isothermal block. I will show you in the next figure. Using isothermal block at the point of connection keeps these junctions in thermal equilibrium and produces equal and opposite EMF. So, cancelling that will not come in the net output voltage, or net EMF voltages. Therefore, the measured voltage is the difference in potential between the measuring junctions and the isothermal block, which serves as the reference junction. You see here, fine. I have a thermocouple with material A, right. Let me take this one. So, this is a metal A, I mean it is a alloy A, it is alloy B, right. This is a measuring junction. So, I have so usually connecting wires are made of copper. So, if these two junctions, because you see the metal A and copper, there is one junction, and this is another junction, this is one junction, this is another junction. So far these two junctions are at the same temperature, that which can achieve this one by an isothermal block. So, there is no change in the net output voltage. Net output voltage we are measuring with this one, because we are connecting with the different wires. So, obviously, if the different wires are connected dissimilar metals, so again thermocouple will be developed. This can be easily managed if these two are put in an isothermal block, that is we talked about. Cold junction compensation. For industrial application, it is impractical to use an ice bath for the reference junction. It is not possible, so it will remain open. By compensating for the voltage developed at the reference junction, the ice point reference may be eliminated. This is achieved by adding a voltage into the thermocouple loop equal but opposite to that of the reference junction. AD594, AD595 are the family of thermocouple signal conditioning ICs that provide cold junction compensations as well as output voltage amplification. It also provides an alarm when the measuring junction is open, that when the junction reference measuring junction is open for cut or some, suppose it is made by welding, suppose welding is broken. So, I need some annunciation, I need some alarm. So, that can be possible also with this particular chip. So, circuit description. So, obviously, you can see that it saves a lot. I do not need additional circuits to make all this, to achieve all these extra features. Figure 5 shows a block diagram of the 8594 590 thermocouple signal conditioners. Type J, which is for 8594 is to be used with a type J, and type K is 8595 thermocouple is connected to the pins 1 and 14 and the inputs to an instrumentation amplifier differential stage. The input amplifier is contained in a loop that uses the ambient or room temperature as its reference. The IC here is also at the ambient temperature, and the cold junction compensation circuit develops a voltage equal to the deficiency due to the non-ice point reference junction. The voltage is then applied to a second preamplifier whose output is summed with the output of the input amplifier. The resultant output is then applied to the input of a main output amplifier with feedback to set the gain of the combined signals. I will show you all this in the circuit. The ice point compensation voltage is scaled to equal to the voltage that would be produced by an ice bath reference thermocouple measuring the ice temperature, IC temperature. So, but this part is concerned, this is very similar to the whatever the old chips we have used 8590, right. Now, some additional features are there. 580 is for stabilized power supply, 590 is actually the thermocouple. These are the latter versions. This is our actual circuits you can look at. This is thermocouple circuits, right. You see here. So, this is we have one amplifier here, okay, another amplifier here. Okay. This is summed up and coming to another amplifier, and see here this overload detection circuit. So, this will give you a alarm here, which is alarm transistors we are using, and some ice resistors are there. So, this is a complete block diagrams or block diagram means I should not say the detailed circuit diagram of the 8594 or 595. This is a block diagrams of 8594. This is a factory trim. So, it has advantages, that means I do not need additional capacity, additional resistors, which we need in the case of 8590. Okay. There is a chart available for particular whatever the particular reference resistors we have to use, but this is not necessary here. So, it is already inside the chip. The voltage is then added with the locally referenced loop voltages, which will make the compensation, right. And though the feedback path through the feedback path, the main amplifier maintains the balance at its inputs. In the case of open thermocouple, these inputs become unbalanced and the fault is detected, and the overload detection circuit drives a current limited NPN transistor that gives an output of which can be as an alarm, which can be used as an alarm, which can be used, I should say which can be used as an alarm, right. Output voltages. To produce a temperature proportional to output, you see that further advantage of this one, that I am getting an amplification of 10 volt per degree centigrade. It is quite high. Usually, you know that this thermoelectric power, usually that means that sensitivity to thermal is quite low. It varies typically, suppose from 60 microvolt per degree centigrade to 12 microvolt per degree centigrade. In the case of Cromwell constant, and it is coming around 60 microvolt per degree centigrade, whereas in the case of platinum, rhodium, platinum thermocouple, it is 10 to 12 microvolt per degree centigrade, which is quite low. But here you see at the outputs I am getting 10 volt per degree centigrade. So, sensitivity is extremely high, you can see here 10 millivolt per degree centigrade. You can see here this sensitivity is quite high. So, it is already signal process and we are getting so much of sensitivity here. So, the resolution obviously will increase. So, provide and to produce a temperature proportional output of 10 millivolt per degree centigrade, provide an accurate reference junction over the rated operating temperature range. AD594, AD595 is again trimmed during the manufacturing to match the transfer characteristics of type J and K thermocouples at 25 degree centigrade. At 25 degree centigrade calibration temperature, the sensitivity are 51.7 microvolt per degree centigrade for type J and 40.44 microvolt per degree centigrade for type K thermocouples respectively. This gives the gain of 193.4 for AD594 and 247.3 for AD595 to realize a output of 10 millivolt per degree centigrade output. Okay. Although the device is trimmed to give an output of 250 millivolt, an input offset error is induced in the output, an amplifier resulting in offset of 16 microvolt and 11 microvolt for the AD594 and AD595 respectively. The actual output can be calculated using the following equations. What are the equations? Output of AD594 voltage J type plus 16 microvolt multiplied by 193.4. Okay, this is the actual output voltage I will get from this circuit. And in the case of AD595, I will get a output 8595 voltage K type plus 11 microvolt into 247.3, where the type J and K voltages are taken from table reference to 0 degree Celsius. All the tables are available. So, I am for the reference I am giving this table. Okay. So, is J and K. J is the iron constant and K is the chromium level. These are the most widely used thermocouple in industry. So, maximum temperature range 0 degree to 750 degree centigrade. So, within that range I am getting a 0 to 42.283 millivolt, and in this case 5.973 to 50.633 millivolt, right. So, this is the range I am getting of voltage swing I am getting. Thermocouple output is linear only over a narrow temperature, that is thermocouple is a non-linear devices. Over a short range only I will get a linear characteristics, but however it is a non-linear. If you take a wide range, it is a, if you can express the polynomial equations that I told you earlier also. Okay, it looks like if I take it C naught, sorry, output voltage E naught equal to A T plus B T square plus C T Q, right. So, T is the temperature difference between the two junctions. So, it is a non-linear, you can see this one. So, for only for sometimes you will find it can be 7 degree polynomial, okay. Sometimes you will find it can be represented by the 8 degree polynomial. So, it is a highly non-linear devices. Only in the case of platinum rhodium platinum thermocouple you will find that it is 2 to 3rd degree polynomial, it can be represented by. AD594, AD595 do not provide linearization. Linearization technique implemented externally when it is to be used over a wide temperature range. Optimizing performance. By following certain precautions or adding additional networks, the performance of the chip can be enhanced or optimized. Cold junction error, this is one error. Optimal performance from AD594, 595 is achieved when the thermocouple cold junctions and the IC chips are at thermal equilibrium. It should be at the same equilibrium, that means cold junctions. So, if we put usually if I put the AD594 and AD595 very close to the isothermal junction, that means where I am taking the connecting the copper wire from the alloy wire of the thermocouple. So, this will satisfy this statement cold junctions, the cold junction errors will not be there. By avoiding the placement of heat generating devices or components near the chip, this can be achieved. Okay. So, we cannot, if I put far away any heat generating like transformers or any that type of things, that can be easily achieved. This problem can be easily solved. Soldering. The proper soldering technique is to be implemented to bond the thermocouple to the printed circuit boards. Okay, proper, with typical flux and whatever the thing, that means there should not be any dry soldering, that type of thing. Cleaning the thermocouple wire to remove the oxidation before soldering helps, because you see the thermocouple, some of the thermocouples like iron constants are very prone to oxidation. Okay, so that so if it is prone to oxidation, we must clean it before soldering, because two junctions is to be, two wires is to be soldered, either solder or welded, whatever it may be. Okay. Even if you can just tie like this one, two wires, so it will work, but I need, for physical strength, I need either soldering or welding. So, soldering, if you do, you should first clean up those junctions, those portions, then we weld or solder it. Basic current return. The input instrumentation amplifier of the chip requires a return path for its input bias current, and this should not be left floating. If the thermocouple measuring junction is electrically isolated, then the pin 1 of the IC should be connected to pin 4, the power supply common. In some cases, tying the thermocouple directly to the common is not possible. A resistor is connected between pin 4 and pin 1. We will satisfy that bias current return path, but will however generate an additional input offset voltage due to the 100 nanoampere bias current flowing through it. If it is the grounded thermocouple, or if it is a small common mode potential is present, it is recommended not to connect pin 1 and pin 4 together, right. Now, last of these particular lessons, we will discuss some programmable isolated voltage to current converters 1B22. Okay. This is also many places we need, because we cannot transmit current, we cannot transmit voltage, we have to always transmit current. So, I need this type of converters in many places. Whenever I am getting a signal, pneumatic signals or anything which is to be converted in voltage first, then to transmit to the actual point of control, that which is mostly for the PC. So, I need a voltage to current converter. So, all these things can be achieved by this chip 1B22. Let us look at the details of this one. Features: internal isolated loops, supply drives 1000 ohm load. So, it has a large load, it can be supplied. Pin programmable inputs, I can have 0 to 5 volt or 0 to 10 volt input, I can have two 0 to 5 volt. Usually typically you will find in process or in industries, you will have two types of, either 0 to 5 volt, 0 to 10 volt. Output I can have either 0 to 20 or 4 to 20 milliampere. So, pin programmable outputs, pin programmable inputs and pin programmable outputs 4 to 20 milliampere or 0 to 20 milliampere. High input to output isolation, okay, high input to output isolation, okay, 1500 volt RMS. So, it is a large isolation, that is very much necessary, okay, to to satisfy to protect my other instruments. Normal mode output protection, that is 240 volt RMS. Low nonlinearity, it is plus minus 0.02%, that is also great advantage. High CMRR, it is 90 dB. So, common mode rejection ratio is quite high. General description: 1B22 is an isolated voltage to current converter that incorporates transformer isolation to achieve high performance and automated surface mount manufacturing for low cost and increased reliability. The voltage to current converter consists of 4 basic sections. We have input conditioning circuits, we have modulator, demodulator, we have isolated loops, we have supply and current source. These are the basic blocks. The 1B22 is a pin programmable for 0 volt to 5 volt or 0 volt to 10 volt inputs and 0 to 20 milliampere or 4 to 20 milliampere outputs using an internal resistor network. It can also be set by an external resistor to accept 0 volt to 1 volt or 0 volt to 10 volt input. The transformer coupling provides 1500 volt RMS galvanic isolation between the inputs and the current loop. The low power is generated internally through the DC-DC converter and is also isolated from the input side, which is 1500 volt RMS. Loop compliance voltage is dependent on the voltage supply to the 1B22, that chip, and with V loop equal to 28 volt, it is sufficient to drive a 1000 ohm load. It can operate as a very wide temperature range. It has two type of chip are available. One is for commercial, which is minus 25 degree centigrade to 85 degree centigrade. Industrial range is minus 40 degree centigrade to 85 degree centigrade. This is resistor network. you see these are our basic block diagrams of our these isolations. You see the power isolation, there is a signal isolation. So, all these isolations that are there in this particular, we have oscillators here. Okay, this is our entire chip, okay, of this 1B22. This is an input 1 and input 2, you can see, which is coming. A 4 milliampere is to be this one. The conditioned the signal is modulated to generate a square wave that drives the transformer T1. The peak to peak amplitude of the signal is proportional to V in. This is the transformer T1, please note. This is the transformer T1, this is the transformer T1 and this is the transformer T2. This is the transformer T1 and this is the transformer T2. The conditioned signal is modulated to generate a square wave that drives the transformer T1. The peak to peak amplitude of the signal is proportional to V in, right. So, that is actually what we want. An internal high stability reference with a nominal output voltage of 6.4 volt is used to develop a 4 milliampere offset for the 4 to 20 milliampere of current loop output. After passing through the signal transformer T1, the amplitude modulated signal is demodulated and filtered by a single pole filter, that means first order filter. This filtered output is the control signal for the voltage to current converter stage. The timing informations for the demodulator is provided from the power transformer T2. The 1B22 outputs are protected from the accidental short circuits to AC line voltage up to 240 volt RMS, that is already specified. Now, DC to DC converter consists of a power drive, power transformer T2 and a full wave rectifier and a filter, right. Now, this DC to DC converter provides the power for the output circuitry as well as the isolated components voltage for the loop, and this voltage is proportional to V loop on the input side, right. So, this will give everything, this will give the our power supplies also. So, the DC to DC converter is necessary. The 1B22 requires a plus minus 15 volt supplies to power the input side circuitry and plus 14 volt to plus 30 volt supply for the DC to DC converter. So, basic interconnections we can see here, the basic interconnections are shown in figure. Next slide. For 0 to 5 10 volt signals, either IN1 and or IN2 can be used for input. For 0 volt to 5 volt signals, jumper IN1 to IN2, right. So, this is to be shorted. For 4 to 20 milliampere of operation, the 4 milliampere, this also we call is the pre-programmable, right, programmables in that sense. That means input is programmable and that is output is programmable here. For 4 to 20 milliampere operation, the 4 milliampere offset node should be jumped to the S node, while for 0 to 20 milliampere operation it should be tied to the common, right, because 4 milliampere is not necessary. The functional diagram of the resistors networks in the 1B22 is shown in figure 8. This is our functional diagrams. Okay, you can see here how it works actually. Input 1 and input 2, this is a resistor network 4 milliampere offset. Okay, so, we are using some capacitors here. So, we have a transformers, we are showing like this one, these are the basic two transformer T1, this is our T2, this is a rectifier loop supply. You can see here, so how the resistors networks are connected, right. These are resistor networks in 1B2, this particular chip. What are the internal networks? These are all inside the chip, you can see. We have a 6.4 volt reference voltage which can be generated by Zener. Applications, we have a lot of applications. We have multi-channel process controls, we are using this particular chip. Okay. This multi-channel process controls, we can have a, in process controls we always need this conversion from 0 to 5 volt to 4 to 20 milliampere of current. So, that is possible. DA converter, current loop interfaces. Then we have analog transmitters and controllers. where I have to transmit that signal many places, even though it is digital, but transmitter is analog, because to the computer when it will go, it has a data acquisition systems at the input. So, it will convert in the digital domain, but before that from the sensor through the transmitter it will go. So, the transmitter itself, this 4 to 10 this 1B22 will be incorporated within the transmitter. That means, which will convert, so like pH, suppose pH whatever the voltage I will get, that convert to the current of 4 to 10 milliampere, that can be achieved there. Remote data acquisition systems, this also can be used, because it has a transmission capacity of over a large distance of 4 to 20 milliampere, even though current is, that can be sensed, that can be used as a data acquisition signal. So, all these features are there in the case of this particular chip. So, these had several advantages, this particular chip, because always you are getting a stable 4 to 20 milliampere of current in these cases, right. And with this I come to the end of this particular lesson.